All right, in this next one, we're graphing the absolute value. Remember, absolute value is in this format. Y equals A times X minus H plus K. And so the important thing to note here, kind of like point slope form, when we see that minus sign, it's like an opposite. There's only a minus sign here, so that one's the opposite, but this one is not the opposite, all right? And that HK is the vertex. And so as we look at this thing, we would say for this one, the vertex, it's the opposite of this guy, which is -3. But then we just take this guy exactly the way that's written, which is a -1, all right? And that's the effect that a minus sign or a plus sign in a formula has, okay? The other thing we do is we look at the A value. The A value this time is 1/2. And the A value tells us two things about this. One, it tells us whether the V opens up or down, but it also gives us a general description of the slope for that V, okay? So because the A value is positive, it's going to open up, and we're going to kind of use a slope of 1/2. So here's the quick, easy way to graph this. So the vertex of -3, -1 is right here. This thing opens up with a slope of 1/2, so up 1/2, but I do the same thing, up 1/2 in the other direction as well. I'm creating a V that opens up with a slope that's generally 1/2. And so I keep that going. And there it is. There's my V. There's my absolute value, okay? So it's vertex, A value tells us up or down, and gives us the shape using kind of the slope, okay? And so if I look at this one, the vertex, once again, it's the opposite of this guy. That's a +2. This guy, just as it is, that's a +3. The A value this time is a -2, and that tells me that this thing opens down. It also tells me that this thing kind of has a slope of 2. All right? So as I plot this, 2, 3 is right here. It opens down with a slope of 2. That's down 2/1, but down 2/1 in the other direction as well. Okay, I'm creating a V with slopes of 2 and -2 that opens down. And I could keep that going. That's it. Okay? The other way to think of it, and the reason vertex works the way it does, is because of this idea of shifting things and moving it left, right, up, and down, and that kind of stuff. All right? The original V that we graphed, the original absolute value, started at 0, 0. And when we add on the inside with X, it moves us. Okay, when we add or subtract, it moves us left and right. It always just does the opposite. When I add 3, it moves me to the left 3. And then the -1 on the outside moves me down 1. Likewise, over here, this -2 moves me to the right 2, and this +3 moves me up 3. So when we add or subtract on the inside, it moves us left and right, which it always moves the opposite direction we would expect. But when we add or subtract on the outside, it moves us up or down, and it moves exactly in the direction we would expect, okay? And then the A value, the idea is, yes, the positive versus negative tells us up or down, but those values also tell us if this thing is going to be a stretched or shrunk V, okay? That manifests itself in the form of slope for these, and so we kind of see that stretch and shrink, but we graph it in terms of slope, okay? So applying that same thing here, if I wanted to write the equation of a translation, in other words, an absolute value that's been moved, okay? If I had y equals the absolute value of x, if I want to move this thing up 6.5 units, well, I would just have to put a plus 6.5 on the outside, okay? And essentially, it's saying, hey, instead of having the vertex, we could think of it this way as well, instead of having the vertex at 0, 0, I want to have the vertex 6 units higher, so at 0, 6.5. And then what would that look like when I write the equation? This one, I want to move to the 3 units right and down 5 units. And so once again, we can think of it this way. We said, hey, if we want to move to the right, we have to subtract in here, so I'm going to subtract 3. If I want to move it down, I have to subtract out here, so subtract 5, and that's it. All right? You could also think of it in terms of vertex. Think about it. Instead of having the vertex at 0, 0, if I wanted it to the right 3, I'd want a positive 3 here. And then down 5, I want it at -5. That's where I want the vertex to be. So write the equation now. All right? Here's the opposite of the x value. Here's the y value exactly as it's written. Okay? But that idea of moving this thing and shifting this thing, that's where the idea of finding the vertex from that general format comes from. Okay? If I look at this one, it says to solve by graphing. And so I'm just going to graph each of these. if I were to graph that first one, because it's in standard form, the easiest thing to do is find the x and the y-intercept. So right here, to find the x-intercept, I plug a 0 in for y. So that gives me when I divide each side, that's a positive 3, so it's 3, 0. If I plug a 0 in for x, it gives me the y-intercept. If I solve that, that's a negative 4. So 0, negative 4. And again, that's just for this first line. Let's do the same thing for the second line. If I wanted to graph this guy, well, let me graph that line first. So this way we don't get as confused. And I can even see the slope here after I plot those 2 points. It's up 4 over 3. And I could continue that pattern. Sorry. Got some stray marks I keep trying to erase, but I'm having trouble. Up 4 over 3, so I could keep going up 4 over 3. And now if I graph the other line, once again, x and y-intercepts are the way to go. If I plug a 0 in for x, the y-intercept, let's see, is a negative 6. If I plug a 0 in for y, the x-intercept is a positive 9. And so now, once again, if I plot these, and this might be a little bit hard to plot because we're kind of off the graph a little bit. So 1, 2, 3, 4, 5, 6, 7, 8, 9 is out here somewhere, and negative 6. And so as you look at this, it might be hard to draw a nice graph for this thing. And that's because as we look at this, we're having a little bit of trouble actually seeing where this thing is in terms of it being accurate. But if we kind of think about that, whoops, I erased too much. In terms of the pattern, it's up 6 over 9, so I can see the slope up 6 over 9. Well, that's 6 over 9. I can reduce that. That's 2/3, so I could go up 2 over 3 instead. I could go up 2 over 3. Counting is very hard. 2 over 3, up 2 over 3. And now I can get a much more accurate depiction of this line. Okay? But now solving by graphing, I need to find out where these intersect. Well, it's over here somewhere. It's off the graph. So I might have to extend this a little bit. Ready? Let's see if we can extend this just a little bit. So if I extended this, it's down 4. 1, 2, 3, 4. Back 3, 1, 2, 3. That would be this point right here. And so now I'm just going point by point to see where this matches up. This one would be down 2, 1, 2, back 3, 1, 2, 3. And there it is. It's going to match up at this point right here. And so as I kind of count backwards to that point, if I identify this ordered pair, let's see, negative 6, 7, 8. So that's negative 8 for the y. And looks like negative 3 for the x. Okay? So I had to extend the graph a little bit, and this is why graphing is a little bit tricky sometimes, okay? Because one, if it's off the graph, that causes an issue. If we have fractions, it causes an issue, okay? If they're not in a good format for graphing, it causes an issue, all right? This is why we have multiple methods. Sometimes graphing isn't the best method, and for this particular example, graphing would be good if I had a larger graph, okay? So just extend that graph a little bit, see where they intersect. So for this one, the solution is negative 3, negative 8, okay? And you just leave it as an ordered pair like that. It's telling you that x equals negative 3, y equals negative 8, okay? For this one, solved by substitution. Because this first one is already solved for y, so right here, y equals this thing, it means I can replace this y with a 3 minus 2x, okay? Because y is the same as 3 minus 2x, I can replace any y's with a 3 minus 2x, and so that's what I do. In the second equation, I replace this y with a 3 minus 2x. And now I have an equation that only has x's, and that we know how to solve. I distribute. I combine like terms. And now I continue to solve. I subtract the 6 from each side. I'm going to divide each side by a negative 1. So I end up with x equals 5, but I'm not done yet. I still have to go back, plug that 5 in, and get my y value. So right here, y equals 3 minus 2 times 5. So y equals a negative 7. Okay? And then the last thing I do is I typically write this as an ordered pair, because it's just a nice, succinct way of writing it. If you left it as x equals this, y equals this, that would be fine. That would be technically right, all right? But an ordered pair gives us a nice way of writing it, okay? If I look at the next one, same kind of thing. I want to solve by substitution. So the first thing I need to identify here is, well, which of these things would be easy to get by itself? Which variable would be easy to get by itself? And so we want to look for something that maybe has a coefficient of 1, maybe doesn't have a lot around it being added or subtracted. And so the obvious choice here is this guy. It's this y right here. So I'm going to take that first equation off to the side and say, hey, let's get y by itself. Let me solve for y. So to do that, I subtract the 3x from each side. And we're just rearranging this. I'm isolating y. So I get y equals a negative 3x minus 4. So if y is the same as a negative 3x minus 4, it means I can replace y with a negative 3x plus 4. And so that's what I do in this second equation. I say, hey, let's replace that y. So that's 4x minus 3y, but instead of y, I'm going to replace it with a negative 3x plus 4 equals 1. And now I continue to solve. I distribute. I combine like terms. I add that 12 to each side. And I divide by the 13. But again, the point here is that once you do that substitution, once you plug that value in, I end up with an equation that only has x's in it, which is something we know how to do. And that's kind of the goal a lot of times with these more complicated things. I want to get back to what I already know, all right? I'm still not done. I have to plug this back in and get my y value, and I just plug it in right here. This is the easiest one to plug it into. So I plug the 1 in for x, and now that's negative 3 plus 4, which is a positive 1. So it looks like the ordered pair 1, 1. Okay? If I look at the next one, it says solve by elimination. Remember, elimination, we want to add the equations together and get one of the variables to go away, all right? And so to do that, we need additive inverses. If we look at this particular example, I already have additive inverses in front of the y's. So I can go right to adding these together. If I add these together exactly the way they are, the x's add up to a 5x. The y's add up to 0, so they cancel out. Equals over here, this adds up to a 25. And now I continue to solve. I'm once again left with an equation that only has an x in it, that only has one variable. So I divide each side, so I get x equals a 5. But now I still have to plug this back in and find y. So I'm going to plug it into this first one, so 2 times 5. And it doesn't matter which equation you choose, okay? I'm plugging it into that first equation, and now solving for y. Subtract the 10. And that's it. Write it as an ordered pair. Okay? If I look at the next one, if I'm going to solve by elimination, see, it's not going to work out right now because, one, nothing's lined up. Like, how am I supposed to add those y's together when they're kind of scattered all over the place, all right? And two, if I were to add the x and y, they're not going to cancel anyway. So first of all, I need to rearrange this. So the first thing I'm going to do is I'm going to rearrange this thing. I'm going to say, you know what, let's take that first guy, and essentially I'm working towards standard form. xy equals constant. We just don't care about like all the nitty-gritty details of, oh, you can't have fractions, that kind of stuff, okay? So I'm going to add the 3y to each side. So that gives me a 4x plus 3y equals 7. And so now that first equation's the right format, so if I write the other equation underneath it, see how everything's lined up. That's kind of the first thing we need to do when solving by elimination. Make sure everything's lined up. X, y equals constant. But now I need additive inverses, and so I have to decide, do I want to get additive inverse in front of x or in front of y? Well, it doesn't really matter here. The y values are a little bit smaller. Maybe I'll do the x values for fun, all right? But if I want to get additive inverses here, I have to multiply this equation by something like 7, because that'll turn the coefficient of x into a 28. Well, down here, I have to multiply this guy by something like negative 4, because if I turned the first x into a negative 28, into a 28, the second x I have to turn into a negative 28, okay? And so that's what I do. I multiply by negative 4 to get a negative 28. So here's the result. Here's my equations now. That first equation becomes a 28x plus 21y equals 49. The second equation becomes a negative 28x minus 8y equals a negative 36. Okay? And now if I add these together, those x's cancel out. That's a 0. When I add the y's together, that gives me a 13y. Over here, when I add these together, I get a 13. I divide each side, and I get y equals 1. Still not done yet. I have to plug this back in and solve for my x values and leave myself a lot of space here. Let me do it in a different color so I can see it. I'm going to take that very first equation, the 4x equals 7 minus 3 times 1. And so it's 4x equals, that's going to be 7 minus 3, which is 4. And then I would divide each side by 4. And so once again, I get x equals 1. Okay? And so let me write this answer as an ordered pair. 1, 1. Okay? If I look at this one, it says solve by the method of your choice. And so as I look at this one, I see that everything's all lined up, so I'm leaning towards elimination. I also see that I have some nice values there, the 2 and the negative 1. It's really easy to say, hey, you know what? I can turn the second equation, that second x, into a negative 2 by multiplying each side by 2. And so the first equation, I just leave it the same. I'll leave it the way it is. The second equation now becomes a negative 2x minus 4y equals a negative 6. And now I can add these up. So I add them up. Here I get a 0. The y's also cancel, so I get a collective. Collectively, I get 0 on this side. On the other side, I also get 6 plus negative 6, which is 0. And so this is one of our special cases. I have 0 equals 0. That's a true statement, which means this is infinite solutions. Remember, our special cases are when you get a true statement, it's infinite solutions. If I had a false statement here, if all the variables canceled and I got like 0 equals 10, well, then it would be no solution. Okay? So basically, this is just showing us that, hey, this is the same line twice. It's the same equation twice. So all of their ordered pairs they have in common. So there's an infinite number of very specific solutions. Okay? If I look at the next one I would probably use substitution for, only because nothing's lined up. I don't know how easy it's going to be to get the things to cancel out. So I might take this first one and say, hey, you know what? Let's rearrange this. Let's solve this guy for y by subtracting that 2x from each side. I have a variable that's almost by itself. It's really easy to get by itself, so I'm going to go substitution. And really, if I've rearranged those, if I swapped the x and the y and lined everything up, it would be easy to multiply and eliminate y as well. So elimination would also be good for this one. I just decided to use substitution. And so now I plug that into the second equation, 3x minus 2y, but instead of y, I plug in the negative 2x plus 6. And now I simplify, I distribute. That's a plus 4x minus 12. I combine like terms. Now I'm going to add that 12 to each side. So x equals 4. Okay, I'm still not done. I have to plug it back in over here. So y equals negative 2 times 4 plus 6. That's a negative 8 plus 6, which is a negative 2. Okay, and again, I write my answers in ordered pair. If I look at the next one student bought 3 pens and 4 pencils for $5. Another bought 7 pens and 12 pencils for $13. How much would a student pay for 5 pencils and 4 pens? And so the first thing I need to do, I need to write an equation for each of these situations. So the first student, I'm going to call the pens x and the pencils y, just for simplicity purposes. So what they did is they have 3 times x, so 3 times the amount for each pen, plus 4 times the amount for each pencil equals $5. That's how they get their total bill, okay? The second student, same kind of thing here. It's a 7x plus 12y equals 13. And so if I want to know how much, the end result here is that I want to know how much 5 pencils and 4 pens would be, well, I need to know how much each pen and each pencil are going to cost, okay? And so right now, X is the cost of each pen and Y is the cost of each pencil. I just have to solve this system of equations so that I know how much each one costs. Then I can find out what the price is going to be for specifically 5 pencils and 4 pens, okay? So let's solve this system. As I'm looking at this thing, everything's lined up pretty nicely. So I'm going to use elimination. And for this one, I definitely want to eliminate Y. And the reason for that is because it's a lot easier to turn a 4 and a 12 into the same number than it is to turn the 3 and the 7. See, if I wanted to turn the 3 and 7 into the same number, I'd have to multiply the first equation by 7, and I'd have to multiply the second equation by -3, okay? But if I look at this, all I have to do for the Y's is I have to multiply this first equation. If I multiply by 3, it gives me a 12. Well, I want a -12 since this guy's positive. So I just have to multiply by -3. I have to get additive inverses, and it's much easier to do with Y because it's easy to turn that 4 into a -12, okay? And so it gives me this. -9x minus 12y equals a -15. And now I can add these two equations together, okay? So here that's a -2x, so the y's cancel. Over here I get a -2, and now I divide each side. So here I find that x equals a 1, so the pens are $1 each. I still have to plug this back in and get the cost of the pencils, so I'll plug it into this first one. So from here I solve. I've got to subtract that 3 from each side. And divide by the 4. And don't be fooled here. It is 2 divided by 4, not 4 divided by 2. So that is a 1/2. Although in this context, writing a 1/2 doesn't make much sense here. It's much better to write this as 0.5. Because again, we're talking about money. We're now saying that, hey, the pens cost $1 each, and the pencils cost 50 cents each, okay? Half a dollar, okay? And that's great information, but that still doesn't quite answer the question. That's part of what I needed for the answer, okay? But if it asks me, hey, how much is it going to run me if I buy 5 pencils and 4 pens? Well, let's find out. 5 pencils, those are 50 cents each. Plus 4 pens, those are $1 each. Well, let's see what we get here. Let's see, that's $2.50 for the pencils, plus $4 for the pens. It looks like I'm looking at $6.50. So do make sure that you answer the question. Yes, we needed to know the price of each, but we needed to know that so I could calculate the price of 5 pencils and 4 pens. Okay?